Welcome! In this session, we'll tackle LeetCode problem number 843, guess the word. This is an exciting interactive problem where you'll need to strategically guess a secret word while receiving feedback on the match with each attempt. Let's dive into the challenge and explore how to efficiently solve it. In this problem, you are tasked with playing a word-guessing game where the objective is to identify a secret word. You are provided with a list of potential words, called the word list, and must guess the secret word within a limited number of attempts. To facilitate the game, there's an external API called Master, which provides feedback on your guesses. Specifically, the API includes a method master.guessWord that takes your guessed word as input and returns an integer. This integer represents the number of characters in your guess that exactly match the secret word in both position and value. Your job is to develop a strategy to determine the secret word while making at most 10 calls to master.guess. Additionally, all words in the word list are guaranteed to be unique, and the secret word is always present in the list. The challenge lies in efficiently using the feedback from the API to narrow down the possibilities and identify the secret word within the constraints. The input for this problem consists of a list of unique strings called wordList, where the number of words in the list can range from 1 to 100. Each string in the word list has the same length, denoted as m, where m can range from 1 to 10. It's important to note that the secret word is always guaranteed to be one of the words in the word list. As for the output, there isn't an explicit return value from your implementation. Instead, your task is to use the master.guess method to determine the secret word. Let's look at some examples to better understand how the problem and the API work. In the first example, the word list contains words such as axe, baz, ios, and apps, and the secret word is axe. If you guess axe as your first attempt, the master.guess API will return 6, indicating that all 6 characters match the secret word in both position and value. Since the match count returned by master.guess in this case is 6, it clearly identifies axe as the secret word, and the game ends successfully. Now, consider a second example where the word list includes words like AAA, BBBBBB, CCCCCC, and DDDDDD, and the secret word is CCCCCC. If your first guess is BBBBBB, the master.guess API will return 0, indicating that no characters in your guess match the secret word in either position or value. Based on this result, you can eliminate all words that share any characters with BBBBBB at the same positions. This process of elimination helps you narrow down the possible candidates for the secret word. By continuing with this strategy and making subsequent guesses, you can eventually identify CCCCCC as the secret word. The constraints and edge cases for this problem are critical to consider. The word list always contains at least one word and at most 100 words, and each word has the same length, ranging from 1 to 10 characters. All words in the word list are unique, and the secret word is guaranteed to be included in the list. The master.guess API can be called a maximum of 10 times, so exceeding this limit will result in failure. For edge cases, if the word list contains only one word, your solution must immediately guess it since it is guaranteed to be the secret. Similarly, if the words in the word list are very similar, with only slight differences, your implementation must efficiently narrow down the search space by leveraging the feedback from the API. To solve the problem, your strategy should focus on eliminating words that cannot be the secret based on the feedback, selecting guesses that minimize the remaining possibilities, and ensuring that the solution works within the 10 guess limit. To tackle the guess the word problem, our goal is to determine a secret word from a list using at most 10 guesses. Each guess receives feedback from the master API, which tells us how many characters in our guessed word match the secret word at the exact positions. The challenge lies in minimizing the number of guesses while still accurately identifying the secret word. To achieve this, we need a strategic approach to progressively narrow down the list of possible candidates based on the feedback we receive at every step. One straightforward approach is brute force. The intuition here is simple: guess each word in the list one by one, and use the feedback to eliminate words that don't align with the feedback score. The process involves iterating through the list, comparing each guessed word's similarity score with every other word, and filtering out incompatible candidates. While this method is conceptually simple, it has significant limitations. With a time complexity of n squared, this approach involves a lot of unnecessary comparisons, especially for larger word lists. Additionally, it doesn't prioritize guesses, which can lead to wasted attempts and inefficiency overall. A more refined solution is the optimized greedy strategy, which is the chosen approach for this problem. The key idea here is to prioritize guesses that maximize the amount of information we gain. This is where the minimax concept comes into play. Instead of guessing arbitrarily, we simulate the feedback each word would generate if it were guessed and analyze how it splits the remaining words into groups based on their feedback scores. We then select the word that minimizes the size of the largest group, ensuring that our guess reduces the search space as evenly as possible. By leveraging this method, even if the guessed word isn't the secret word, it helps us significantly narrow down the possibilities, making it a much smarter and efficient approach. This optimized strategy does come with its own computational overhead. The time complexity is n squared, as we need to simulate feedback for each word against all others and group the candidates accordingly. However, it uses only n space to store the filtered word list. The advantage of this approach is its ability to guarantee fewer guesses by prioritizing high-information words. This makes it highly effective for larger word lists where minimizing the number of guesses is critical. On the flip side, the trade-off is that it requires additional computation per guess, which can be more resource-intensive compared to brute force. However, this extra effort is justified by the significant reduction in the overall number of guesses required. Another option is randomized guessing, where we simply pick words at random and use the feedback to filter out incompatible candidates. While this approach is simple and straightforward, it lacks any prioritization, making it highly inefficient and unreliable. In larger word lists, it may even exceed the 10-guess limit, which is unacceptable for this problem. That's why the optimized greedy strategy stands out as the best choice. It balances efficiency and accuracy, ensuring that each guess provides maximum information gain. While it does involve more computation during each step, this trade-off is well worth it to meet the problem's constraints. This approach is particularly advantageous for larger inputs, as it ensures the solution remains within the allowed attempts while systematically narrowing down the possibilities. The problem at hand is to guess a secret word from a given word list, with a maximum of 10 attempts. Each guess is evaluated by the master API, which tells us how many characters in the guessed word match the secret word in both position and value. The challenge lies in using this feedback to minimize the number of guesses needed to find the secret word. The algorithm begins by filtering the word list, which initially contains all possible candidates. The idea is to iteratively reduce this list by eliminating words that cannot possibly be the secret word based on feedback. For the first guess, we don't just pick a random word, instead, we use a heuristic to choose a word that maximizes the chance of splitting the word list into smaller subsets. This approach ensures that each guess provides meaningful feedback, allowing us to narrow the search space effectively. Once we have chosen a word to guess, we submit it to the master API and receive feedback in the form of the number of matching characters. This feedback is then used to filter the word list further. For each word in the current list, we calculate how many characters match the guessed word and retain only those words where the number of matches is exactly equal to the feedback received. This step is key because any word that doesn't produce the same feedback cannot be the secret word and can therefore be eliminated. The process is repeated until either the secret word is identified or the maximum of 10 attempts is reached. If the word list contains only one word at any point, that word must be the secret word, and we can stop early. This iterative process, combined with the heuristic for selecting guesses, ensures that we work efficiently within the constraint of 10 attempts. A critical aspect of the algorithm is the heuristic used to choose words. Rather than guessing randomly, we aim to maximize the information gained from each guess. This means selecting words that, when guessed, minimize the maximum possible size of the remaining word list. By doing so, we ensure that each guess contributes significantly to narrowing down the possibilities. Feedback from the master API serves as the central mechanism for filtering the word list. Each round of feedback helps eliminate words that do not produce the same number of matches, allowing us to systematically reduce the search space. We must also handle edge cases, such as when the word list becomes empty or no valid guesses can be made. In these scenarios, the algorithm should terminate early. Additionally, the algorithm must always respect the limit of 10 attempts, even if it has not yet identified the secret word. The algorithm relies on two key data structures: the word list, which stores the current set of potential candidates, and the feedback from the master API, which indicates the number of matching characters. The word list is updated after each guess to reflect only the valid candidates based on the feedback. A simple list structure works well for this purpose, as it allows efficient filtering operations. The feedback is represented as an integer and is critical for guiding the filtering process. Two primary operations drive the algorithm. First, match calculation. For each word in the list, we compute how many characters match with the guessed word. This operation has a time complexity of O, n asterisk m, where n is the size of the word list, and m is the length of each word. Second, list filtering. Using the feedback, we eliminate invalid words from the list. Together, these operations ensure that the search space shrinks after each guess, making the algorithm both effective and efficient. To better understand the algorithm, let's visualize the flow of data. We start with an initial word list, such as apple, banana, cherry, grape, and a secret word, like cherry, though the algorithm does not know this upfront. For the first guess, let's say we choose apple. The master API returns feedback indicating one match, meaning one character in apple matches the secret word in position and value. Based on this, we filter the list to retain only words that also have exactly one match with apple. Next, we make a second guess, perhaps grape. If the feedback is two matches, we filter the list again to keep only words with two matches to grape. This process continues until either the secret word is identified or we exhaust the maximum of 10 attempts. Each guess and feedback cycle helps refine the word list, bringing us closer to the solution while adhering to the constraints. To optimize the algorithm, we focus on minimizing the search space as aggressively as possible. The feedback from each guess is used to eliminate invalid words, and the goal is for each iteration to ideally have the size of the word list. To achieve this, we use a heuristic that selects the most informative word for each guess, maximizing the efficiency of the search. Pre-processing the word list can also help in cases where the list is very large. For example, pre-computing word similarity metrics can speed up filtering operations. From a complexity perspective, let n be the size of the word list and m the length of each word. Match calculation takes O, n asterisk m, while filtering takes O, n. Since there are at most 10 iterations, the total complexity is O, 10 asterisk n asterisk m. This is highly efficient given the constraints, as the word list size is typically manageable, often around 1,000 words. The code begins by importing the random module, which is not strictly required but can be useful for testing purposes. The find secret word function is defined within the solution class, and it takes two arguments: word list, a list of potential secret words, and master, an instance of the master API that provides the guess method. The helper function count_matches is defined to calculate the number of matching characters at the same positions between two words. This is used to filter the word list based on feedback from the master.guess method. The algorithm executes a maximum of 10 iterations, as specified by the problem constraints. In each iteration, a frequency dictionary is constructed for each character position, 6 positions for 6-letter words. This frequency dictionary is used to determine which word in the current word list is the best guess, where best is defined as the word that maximizes the sum of character frequencies at each position. The master.guess method is called with the best word, and the number of matches is obtained. If the match count is 6, the algorithm terminates as the secret word has been found. If not, the word list is filtered to include only the words that have the same match count with the guessed word. This ensures that the remaining candidates are consistent with the feedback received. By iteratively narrowing down the word list and using the frequency-based heuristic to select the most informative guesses, the algorithm efficiently converges on the secret word while adhering to the maximum of 10 guesses allowed. To solve the problem, we start by creating a class called master with a method named guess. This method is provided in the problem's environment and is used to compare our guessed word against the secret word, returning the number of matching characters. Next, in the solution class, we define the find secret word method, which is responsible for identifying the secret word. The method begins by running a loop for up to 10 attempts, as the problem allows a maximum of 10 guesses. Inside the loop, we construct a frequency map to determine the most common characters at each position across all words in the current word list. This is done using an array of hash maps, where each map corresponds to one position in the words. We iterate over every word in the word list, and for each character at each position, we update its frequency count in the corresponding map. This frequency data will help us choose the best word to guess next. Once we have the frequency map, the next step is to determine the best word to guess based on the frequency scores. For each word in the word list, we calculate a score by summing the frequencies of its characters at each position. The word with the highest score is chosen as the best word, as it is most likely to maximize the number of matches and reduce the word list effectively. After choosing the best word, we use the guess method provided by the master class to compare this word with the secret word. The method returns the number of matching characters. If all 6 characters match, the secret word has been found, and we exit the method. Otherwise, we filter the word list to keep only those words that have the same number of matching characters with the guessed word as the value returned by the guess method. This ensures that the remaining candidates are consistent with the feedback we've received, narrowing down the possibilities. To support the filtering process, we define a helper method called countMatches. This method takes 2 words as input and calculates how many characters match at the same positions between the 2 words. It iterates over the 6 positions of the words, comparing characters at each index, and increments a counter whenever a match is found. The count of matching characters is then returned. This method is used to evaluate each word in the word list against the guessed word, ensuring that only valid candidates remain in the filtered word list. With this approach, we iteratively refine our guesses, leveraging the feedback from the guess method and the frequency analysis, until the secret word is identified or the maximum number of attempts is reached. To solve the problem of guessing the secret word, we start by analyzing the provided word list and the hidden secret word, which in this example is axe. Our first step is to compute the frequency of each character at every position across all the words in the word list. For example, at position 0, the characters at and C each appear twice. Similarly, at position 1, C appears 3 times, while B appears once. This frequency table helps us understand which characters are more common at each position, and it will be instrumental in selecting the best word to guess next. Now, with the frequency table complete, we can move on to using this information strategically to narrow down our guesses. Using the frequency table, we can now compute a score for each word in the word list. The score of a word is calculated by summing up the frequency values of its characters based on their positions. For instance, the word axe scores 2 for the character A at position 0, 3 for C at position 1, and so on, resulting in a total score of 14. The word with the highest score is selected as the best guess, which in this case is axe. We then call the master.guess function with axe, and it returns 6 matches. Since the number of matches equals the length of the word, we know we've found the secret word and can exit the process. In the second example, the secret word is IOs. Just like before, we start with the given word list and compute the frequency of characters at each position. The frequency table for this word list remains the same as the previous example since the word list itself hasn't changed. Using this table, we select the word with the highest score, which again is axe, and call master.guess with this word. However, this time, the function returns 0 matches, meaning none of the characters in axe are in the same position as the secret word. This result helps us filter the word list further. Based on the 0 matches returned from the previous guess, we can now eliminate any words from the word list that have any character matches with axe in the same position. After filtering, the new word list contains only one word, IOs. Since there's only one word left, we can confidently guess it next. Calling master.guess with IOs returns 6 matches, confirming that we found the secret word. The process ends here. Now, we move on to a third example, where the secret word is kbaz, and we repeat the steps to see how the solution works in this case. For the third example, where the secret word is kbaz, we again start by computing the frequency table for the initial word list. The frequency values for each position are the same as in the previous examples. Using these frequencies, we calculate the scores for the words and find that axe is still the best guess. We call master.guess with axe, and this time, it returns 3 matches. This result indicates that 3 characters in axe are in the same positions as in the secret word. Using this information, we filter the word list to keep only those words that also have exactly 3 matches with axe. The new word list now contains kbaz and abks. With the filtered word list, we recompute the frequency table based on the remaining words. The updated table reflects the reduced set of words, with frequencies recalculated for each position. Using this new table, we determine the best word to guess next, which is kbaz. Calling master.guess with kbaz returns 6 matches, confirming that this is indeed the secret word. Having successfully identified the secret word, we can now exit the process. This example demonstrates how the solution systematically narrows down the word list and uses frequency analysis to make optimal guesses at each step. To analyze the time complexity of the solution, let's break it into its main steps. First, we have the frequency calculation. This step involves iterating over the entire word list, which contains n words, and for each word, updating the frequency dictionary for all 6 positions in the word. Since we process 6 characters per word, the time complexity of this step is O n asterisk 6, which simplifies to O n for each iteration. Next, we need to choose the best word to guess. For every word in the word list, we calculate a score by summing the frequency values of its 6 characters. This also involves iterating over all n words and processing 6 characters for each, resulting in the same time complexity, O n asterisk 6, which simplifies to O n per iteration. Both of these steps are efficient and linear with respect to the size of the word list. Filtering the word list is another key step in the solution. After making a guess, we refine the word list by keeping only those words that have the same number of matching characters with the guessed word as returned by the master.guess function. For each word in the word list, we perform a comparison against the guessed word, which involves checking all 6 characters. This operation takes O n asterisk 6, simplifying again to O n per iteration. Since these steps, frequency calculation, selecting the best guess, and filtering, are repeated for at most 10 iterations, as the problem limits the number of guesses to 10, the total time complexity becomes O 10 asterisk n plus n, which simplifies to O 30n. Removing the constant factor, we arrive at an overall time complexity of O n, where n is the size of the initial word list. Now, let's examine the space complexity of the solution. First, we maintain a frequency dictionary that tracks the frequency of characters for each of the 6 positions in the word. Since each position can store up to 26 entries, corresponding to the 26 letters in the alphabet, the space required for this dictionary is constant, O 6 by 26, simplifying to O 1, because it does not depend on the size of the word list. Next, we have the filtered word list. In the worst-case scenario, the word list remains unchanged after filtering, meaning we store all n words, each of length 6. This requires O n asterisk 6, simplifying to O n. Finally, temporary variables such as the best word to guess and the number of matches require only constant space, O 1. Combining these, the space complexity is dominated by the storage of the word list, leading to an overall space complexity of O n. Analyzing the best, average, and worst cases provides additional insight into the solution's efficiency. In the best case, the secret word is guessed correctly on the first attempt, requiring only 1 iteration, which takes O n time. In the average case, we make about 5 guesses, which is half the maximum allowed. The time complexity remains O n, because the number of iterations is a fixed constant and does not affect the asymptotic complexity. In the worst case, all 10 guesses are used, but the time complexity still remains O n, because the fixed number of iterations ensures linear scaling with respect to the word list size. Comparing this to a brute force approach, where each word in the word list is guessed sequentially until the correct one is found, the brute force method would require O n asterisk 6 operations for each guess and up to n guesses in the worst case, resulting in a time complexity of O n squared. This highlights the efficiency of the optimized approach. The optimized approach improves over brute force by strategically filtering the word list and selecting the best word to minimize future possibilities, capping the number of guesses at 10. This dramatically reduces the time complexity to O n. Mathematically, this is because the number of iterations is fixed at 10, and each iteration involves O n operations, resulting in O 10 asterisk n, which simplifies to O n. In terms of space complexity, the solution is proportional to the size of the word list, requiring O n space to store it. By combining these insights, we can confidently conclude that the optimized solution is both time efficient and space efficient, with linear complexities for both time and space. A common pitfall in solving the guess the word problem is making random guesses without any strategy. Random guessing doesn't effectively use the feedback provided by the master API, which means you aren't narrowing down the list of possible words efficiently, and this wastes your limited attempts. Another mistake is ignoring the feedback altogether. The master API gives you the count of matching characters between your guess and the target word, and this information is crucial for filtering out words that can't possibly be the target. Without leveraging this feedback, you risk making unnecessary guesses. Additionally, when multiple words have the same match count, failing to prioritize your guesses strategically can lead to wasted attempts. Instead of guessing blindly, you should evaluate the candidates carefully. Lastly, some people pre-compute all pairwise matches for the word list up front. While this might seem like a good idea, it increases the time complexity to O(n)(, which can be impractical for large datasets. It's better to calculate matches dynamically as needed to optimize performance. Overcomplicating the algorithm is another common mistake to avoid. While it might seem tempting to include elaborate heuristics, overly complex solutions can lead to bugs and consume precious time during an interview. Instead, focus on a clear and effective approach. One key insight for solving this problem is to iteratively filter the word list based on the feedback from the master API. After each guess, narrow down the list of potential candidates by eliminating words that don't match the feedback. To make your next guess, consider words that maximize the chances of reducing the remaining candidates. A common heuristic is to choose a word that splits the list into roughly equal-sized groups based on the feedback it would generate. This helps you eliminate as many possibilities as possible with each guess. Remember, the goal is to balance efficiency and accuracy. Be ready to explain your reasoning clearly to the interviewer, as they will assess your ability to justify your choices. Finally, practicing similar problems, such as other word games, can help you build the intuition needed for filtering and narrowing possibilities systematically. The guess the word problem shares similarities with other word-based problems you might encounter, such as LeetCode 127, Word Ladder, and LeetCode 126, Word Ladder 2, both of which involve transforming one word into another. Another related problem is LeetCode 269, Alien Dictionary, which focuses on ordering characters based on constraints. These problems can help you build problem-solving skills in areas like filtering and pathfinding. When considering alternative approaches to solving guess the word, one option is randomized guessing. This involves making guesses at random and filtering the word list based on feedback. While simple to implement, this method is inefficient and often exceeds the maximum allowed attempts. A more effective strategy is greedy partitioning. Here, you choose guesses that maximize the number of candidates eliminated after each attempt. Although it's more computationally intensive, it significantly improves efficiency. Another option is the most common matches strategy, where you select words with the most common characters among the remaining candidates. This balances simplicity and effectiveness, though it may not always minimize the number of guesses optimally. Understanding these trade-offs will help you tailor your approach to the specific constraints of the problem. Great job! To recap, we tackled guess the word by applying a systematic elimination approach based on feedback. We learned how to optimize decisions within constrained attempts and reduce the problem space efficiently. Thanks for watching. Don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!